Hi, my name is Peter DeCurtins. I'm a senior software engineer here in Boulder, Colorado. I work mostly with the Envy and Jaguar product lines. Also do a lot of geospatial work. And I'm a blogger at our Imagery Speaks blog. My last couple of entries have talked about issues of navigation and positioning, geography. So I thought that I'd put together a little short presentation that delves into some of the basics of, that lie at the fundamentals of geodesy, which is the subject which involves itself with determining the shape and form of the Earth, and cartography, which is the science that we apply to mapping the Earth. So we start out with our old friend the globe, which is very handy for examining geographic spaces. Because it is a three-dimensional spherical object, basically you can see that directions, distances, shapes, areas, all those good quantities that are associated with mapping are preserved. They're constant and they remain true on the globe. However, the globe is very, very small scale, so only very large scale features are really appropriate to view on it. It's not very convenient to put it in your pocket and walk around with it. So we like to have maps. And how do we do that? How do we actually take a three-dimensional object like the Earth and how do we display it correctly with a minimum of distortion or error on something like a map? When we talk about the shape of the Earth, actually, it's not a sphere. It's not a true globe. It's something that's termed an oblate spheroid. It's flattened at the poles, kind of squished in and bulges out at the equator. That's due to its rotation. Things like a globe or an oblate spheroid are smooth, but we also know that the surface of the Earth, isn't anything but smooth. It's got valleys, ridges, oceans, mountains. So there's this term, something called the geoid, which was first identified by C.F. Gauss, and he called it the mathematical figure of the Earth. It's very interesting. It's determined by the gravitational potential field at every spot on the Earth. And gravity does vary. If you're over the Marianas Trench, which is the lowest spot on Earth, it's a very deep valley that's underneath the ocean. The field of gravity is actually a little bit weaker than it would be if you're standing on one of the massive continents, or if you're over the Himalayas or here in the Rocky Mountains up on top of a large mountain. There's a lot of mass that's gathered there, so the force of gravity, the equipotential is stronger in that location. So when you actually measure this with great detail and measure the gravitational field all around the Earth, you get this smooth but highly irregular surface, which really does come as close as you're probably going to get to having a mathematically valid shape of the Earth. And it also corresponds, and this is what I think is kind of neat, with something that's called mean sea level. It's not the actual sea level, but it's the theoretical average level of the oceans if they were connected, if they weren't separated by continents. Like, for instance, if you had canals that dug through the continents and connected all the oceans. The actual mean sea level that they'd kind of settle at is roughly exactly the same level that this geoid is. And in looking here at a small local area, an example of a point on the Earth, you can see, yeah, we do. We have some sea here on this side and this side of a mountain that goes up and rises in between them. And the geoid, which is represented by this heavy black line, yeah, it does. It follows along real close to the surface of the actual surface of the water there. And it rises up a bit here because this big mountain is increasing the force of gravity right there. But we need to get, in order to do mapping, we can't just rely on the geoid. We need to get something that's called a reference ellipsoid. And that's a mathematically defined surface which approximates the geoid in some way. Now, we can choose a reference ellipsoid that really lines up pretty well with the geoid in some small area, like of the Earth, like we've kind of got modeled here in this cartoon. Or we can choose a ellipsoid which does its best to approximate the geoid over the entire globe. And that's the case that we have here in something called the WGS-84 ellipsoid. Now, WGS stands for World Geodetic Survey. 1984 was the major update to that World Survey, and it defined an ellipsoid that serves as the basis for an entire coordinate system. And it's called a geographic coordinate system because it's a coordinate system that's based on a reference ellipsoid. So we're dealing with a three-dimensional surface, and which is this ellipsoid, and we've got a coordinate system, which is latitude and longitude, that lays out a grid on this surface so we can locate ourselves somewhere on it. And then there's a third coordinate, height, or z, represents the height above or below this reference ellipsoid that's been defined. And then there's something that, in order to be, a valid coordinate system, you need more than just an ellipsoid and some coordinates. You also need something that's called a datum, and that's the math that goes into defining just where this ellipsoid actually ties into the Earth. So in our model here, that would be the point wherever this ellipsoid dotted line actually intersects the actual real true surface of the Earth. It's what locks our mathematical representation of the Earth, or a portion of it, to the actual reality that we see on the ground, which is what we're trying to model in a map. So WGS-84 is very prevalent. It's a lot of data that's got geographic information in it that's tied to this coordinate system. It's the basis for the GPS system that is so ubiquitous today. And so it's all very good. It preserves, just like any good geographic coordinate system would, all these aspects. And it's very good for navigation. But when it comes to actually wanting to look at something on a flat surface like a piece of paper or a computer screen, we need to get into what are called projected coordinate systems. We actually need to take that three-dimensional surface and project it out onto a flat surface, which is going to introduce some sort of distortion. Can't be done otherwise. So the art of being a cartographer, one of the key skills anyway, is to select, a correct ellipsoid and a correct projection that will minimize the distortions in the certain areas that you want your map to serve. So Mercator projection is also very common. It's named after the guy who created it, Gustav Mercator. And it's a type of a cylindrical projection. Conceptually, you take this ellipsoid that's been defined, and you consider it to be in a cylinder, which contained within the cylinder and only touching the edges of the cylinder at one line that goes around the Earth, that being the equator. And when you unroll this cylinder into the flat sheet, you see this grid called the graticule makes an evenly spaced, perpendicular, orthogonal grid of latitude and longitude lines. And the reason why this has been so useful and is so prevalent is because in this case, and when you do this, directions are preserved. They're not distorted. So a line that's drawn between 2 points, straight line, represents the actual bearing that a navigator would take to get from point A to point B. Now it does distort other things, significantly area, at any significant distance north or south of the equator. So if you've ever looked at a Mercator world map, you'll notice that the polar regions, high up in the north and way down in the south, they grow very large. They're huge. So it's not a great map for a lot of other purposes other than navigation, but because directions or bearings are preserved, it is highly useful. But there's another type of Mercator projection, a flavor of that's called the transverse Mercator. In that case, you take the cylinder and you rotate it on its side. So you still have the equator going around, but now what's touching the edge of the cylinder all the way around is a chosen meridian or line of longitude. So when you unroll this thing now, what you get is a map that preserves areas in all cases. So we don't have these blow-ups of places like Greenland or Alaska or Australia. And though it does introduce distortions in distances and direction and shape, the other things, it's reasonably accurate within a kind of a thin band that follows that central meridian. So this ends up being a very highly useful projection. It's been used and applied in something that's called UTM, Universal Transverse Mercator. And this basically splits the entire globe up into a number of narrow bands that go north and south. And there's zones. Those zones then are split into northern regions and southern regions, north and south of the equator. But basically any spot on the Earth can be represented in a two-dimensional map with XY coordinates in this universal transverse Mercator for that narrow band. And so you'll often find that we've got maps that are denominated in this coordinate system. So it's real common. So WGS 84, UTM, one of them is a geographic coordinate system. The other one is a projected coordinate system. They're both highly useful and very common. You're likely to encounter them in your work. That's basically what I have to present today, and I appreciate you dropping in and listening. Thanks.